AI generation is starting to break out of the one model, one modality phase and into something much more interesting. Systems that can keep quality high while generating in a single pass on real hardware and across video, 3D, and images. The big shift here is not just speed, it's that researchers are solving the failure modes that usually appear when you push generative models toward autonomy. If you care about where production-grade generative AI is headed, the next few minutes are the useful part. Let's explore the first paper, AAD-1 Asymmetric Adversarial Distillation for One-Step Autoregressive Video Generation. AAD-1 from SJTU, Ant Group, Tsinghua University, Zhejiang University, and Anyverse Dynamics tackles one-step autoregressive image-to-video generation by breaking the symmetry between generator and discriminator. The causal generator preserves streaming inference, while a bidirectional discriminator with a video-level holistic logit can see the full spatio-temporal rollout and detect motion collapse and long-range drift that causal critics miss. The method combines a three-stage training recipe, ODE initialization, a self-rollout distribution matching warm-up, and asymmetric adversarial refinement on top of the public WAN 2.1 T2V14B backbone using sync tokens, a sliding window of 9, and a single sampling step per chunk. On vBench I2V, the final one-step model reaches 94.34 subject consistency, 95.08 background consistency, 98.22 motion smoothness, and 98.65 I2V subject faithfulness, outperforming prior autoregressive baselines such as CosVid and self-forcing while matching or exceeding the bidirectional WAN 2.1 reference on several consistency metrics. The ablations show why the design matters. Without DMD warmup, aesthetic quality drops to 53.63 and imaging quality to 62.81, while a causal frame-wise discriminator collapses to static video with a dynamic degree of 1.08. The best regularization is lambda equals 20, because lambda equals 0 causes training collapse, and lambda equals 50 introduces grid artifacts. The paper also reports that full training takes about 3.5 days on 64 NVIDIA H20 GPUs, and one-step inference on a 14B model runs at 1.134s and 14.33 frames per second on a single H100 GPU. Let's explore the second paper, Meshweaver Sparse Voxel, Guided Surface Weaving for Autoregressive Mesh Generation. Meshweaver from Tencent PCG's Arc Lab reframes autoregressive mesh generation as sparse voxel guided surface weaving and shifts prediction from next coordinate to next vertex, which shortens token streams and improves topology-aware reasoning. The core design combines a hierarchical sparse voxel encoder with a multi-level vertex tokenization scheme. Voxel features serve as vertex representations, cross-attention injects local geometry at each refinement level, and occupied voxels act as a generation scaffold that masks invalid predictions. Trained on an 800K mesh corpus built from Objaverse++, ShapeNet, 3D, Future, HSSD, and ABO, the model uses a 2-4 layer Llama 3 style transformer with 600M parameters and 7-bit quantization. On point cloud condition generation over the Toys 4K benchmark, it reduces chamfer distance to 0.116 and Hausdorff distance to 0.087, while reaching 0.732 normal consistency and 0.914 absolute normal consistency. Its vertex-level tokenization achieves a state-of-the-art 18% compression ratio compared with prior methods capped at about 22%, and it scales to meshes with up to 16K faces. An ablation further shows that cross-attention KV caching increases inference throughput from 26.8 to 30.7 tokens, a 14.5% gain. Let's explore the third paper, Rank End-to-End Post-Training for Discrete Text-to-Image Generation with Decoder Co-Evolution. Ranky from Westlake University, Zhejiang University, Tsinghua University, Hong Kong University of Science and Technology, and Shanghai AI Lab is a first end-to-end post-training framework for discrete text-to-image generation that targets a failure mode. The paper calls latent covariate shift. Reward optimization improves the autoregressive policy, while the frozen VQ decoder drifts out of its training distribution and image fidelity collapses. The method alternates between GRPO-based policy updates and decoder adaptation, using a ranking objective at 2 levels: token-level group relative advantages for the policy and pixel-level reward-weighted rank GAN plus direct reward backpropagation for the decoder, while anchoring the decoder with reconstruction and EMA consistency regularization. On LlamaGen XL at 775 M parameters, Ranky breaks the usual clip-fid trade-off on MS Coco 30K, reaching 33.76 clip and 15.21 fid, versus standard RL's 32.45 clip and 17.76 FID on Janus Pro 1B. It also improves clip to 33.86 and lowers fid to 25.19. The mechanism is supported by diagnostics, showing standard RL widens token distribution, KL divergence by 24%, and reduces codebook entropy, while Ranky keeps both near the SFT regime. Ablations confirm that removing rankan, reconstruction, consistency, or reward backpropagation degrades performance, and the full method is trained on 8 times NVIDIA, a 100 GPUs, with a 16,384 entry codebook over a 15K caption corpus. That's a wrap on today's AI paper highlights. Thanks for watching.